Hello, I'm Nick Tholen, and I'm going to talk about my role on the Maple Seed team, a multidisciplinary program project. The goal of the Maple Seed team is to gather more accurate atmospheric data than radar or LiDAR can by having a series of small sensors in the atmosphere. The Maple Seed team is actually broken down into four main sub-teams. The first is the Maple Seed Flyer team, which develops a flyer that takes on the shape of a maple seed in order to remain in the air for a longer time and gather more atmospheric data. They also work on the writing and preliminary testing of code operating the flyer PCB. The second team is the drone-based optical microscope team. What they do is they have a drone that flies around in the air and collects particles from the air, and then uses image recognition and machine learning software to determine what the particles are. Another team is the 3D printed PCB team. Their goal is to create cheap 3D printed PCBs for use in the Maple Seed Flyers. And the last team is the micro airplane sensor carrier team. This is the team that I'm involved with, and their goal is to carry one of these sensors and fly around for a while and gather more atmospheric data than the Maple Seed Flyer can by remaining in the atmosphere for a longer time. As I mentioned, the micro airplane can remain in the air longer than the Maple Seed Flyer because it's powered. And you might be wondering why not use a drone to carry around the sensors. And that's because the micro airplane can be a lot more efficient by kind of being able to coast around instead of having to constantly be held up by the four rotors that a drone has. And so this allows for the micro airplane to collect more atmospheric data in a more efficient way. And the micro airplane can also be stored in a much smaller way. The image on the right shows a bottom looking up picture of our overall design for the micro airplane team. The design currently uses an Arduino Nano to control the servos, and a manual remote control is currently controlling the airplane. We're using a lightweight 2S battery to control all the motor and the servos. And our overall design really prioritizes minimizing weight in order to fly such a small airplane and be able to take the weight of the battery, which is still a significant amount. Our airplane has 4 control surfaces, 2 in the front and 2 in the back. All those are controlled by the servos. You can see the arrows pointing to them. And the overall structure is with a carbon fiber tube that gives it the right strength, but it remains lightweight. Another important aspect of the design is that the wings are able to fold on top of each other for compact storage so that these airplanes could be taken up into the atmosphere and then released and allowed to coast down. So the folding mechanism design has had many iterations over the time that I've been on the team. In the beginning, in the first design, shown in the top right, the wings were controlled by a motor and they didn't overlap, they just folded in next to each other. Some negatives to this was that this was a heavy design, it required a motor, and it wasn't as compact as it could be. The first redesign that I worked on was the sliding collars that ride in slots, and this was really nice and robust, but it was difficult to integrate with the body because it was so tall, and it was also kind of heavy because it was a larger part. So despite being very robust and working well, we needed to iterate on it further, and that's when we came up with the latest design. This design is more integrated with the body. It's quite a bit more simple, and it's also a lot lighter than the other designs. As a consequence of this, it is less robust and not quite as solid as the previous design, but it doesn't need to be too strong because the overall airplane is quite light itself, so there's not a huge amount of force acting on it. We were fortunate to be able to fully assemble the prototype and begin testing on it. As you can see in the picture in the top right, we're operating our control surfaces. The right wing is currently going up, and we did notice when we were testing all the control surfaces that the rear controls were not super robust and likely to break if it crashed. And so we thought that maybe in the future we'd need to do some redesign on that. We were also able to do our first flight, which was not exactly successful. It crashed pretty quickly, but we did learn a lot from that. And we saw that it did start to pitch upward, which could be a good sign, meaning that it's getting lift, or it could be a sign that there's too much weight in the rear. So we'll have to do some more testing. The day that we tested, it was extremely high winds, and so it was not a great conditions to be testing in, and so we'd like to redo that. There's definitely room for improvement on the design that we currently have. As I mentioned before, there needs to be better control of the rear wing and a more robust design. We also would like to do more testing, especially on conditions that aren't as windy, perhaps indoors. And then we also need to do some more wire management. So as you can see in the bottom picture, the wires are kind of all over the place and the battery is not very well secured. Then we also need to integrate the sensors for atmospheric testing, as I mentioned at the beginning in the overview of the projects. And then we'd also like to be able to create an autonomous flight controller so it doesn't need to be constantly controlled by a person. That way there could be a large deployment of all these to gather a large amount of atmospheric data. I'd like to thank Professor Liang as well as my teammates on the micro airplane team. I'd also like to recommend to anyone thinking about MDP, you should definitely do it. I would definitely recommend doing it myself, and especially if it's the Maple Seed team. Thank you for watching my presentation.